All right, this is our just-in-time lecture covering the most often missed questions in 11.5, Molecular Orbital Theory, second period, Homonuclear Diatomics. Which is an example of a homonuclear diatomic molecule from the second period? All right, the key to this one is homonuclear means same element, same nucleus. All right, and the best answer here is fluorine. Remember, hydrogen is not in the second period, it's in the first period. Calculating the bond order of Li2, diatomic lithium. All right, so we can tally up all of the bonding and anti-bonding electrons. So one way we could do this is to say we've got 1, 2, 3, 4, 4, bond order equals 1/2, number of electrons in bonding minus the number in the anti-bonding. So 1/2 times 2 equals a bond order of 1. Or we can just recognize that these are going to be core electrons, and because they're going to cancel each other out, we could just calculate the bond order using this upper 2s diagram. So we could say that the bond order is 1/2, 2 electrons in a bonding molecular orbital, none in an anti-bonding, so we still get that bond order of 1. All right, when we have this head-to-head overlap along the x-axis, that's always going to be a sigma overlap. So we do borrow some of that valence bond theory language and apply it to what we're learning in molecular orbital theory. All right, a lot of language going on here. Let's break it down. Which statement best describes an anti-bonding molecular orbital? So we're looking for something that's going to have a star on it. So right away, my inclination is to go down here and look at everything that doesn't have a star and go ahead and just cross it out. Okay. And then we see that we have this head-to-head overlap, which we know is going to be sigma bonding. All right, everything's still sigma, so we're looking for that sigma star now. And then the next piece to analyze here, is it going to be higher in energy or lower in energy? If we look at the anti-bonding molecular orbital, we see that as much energy as we offset or lower in this bonding MO, we've got to raise the anti-bonding MO by that much energy. So anything that says lower in energy, we can now cross out. Okay, last piece. Now we have to think about, is there electron density between the atoms? These are the atoms right here, and we see that there is no electron density. In fact, there's this node, and that node says that there is 0 electron density. All right, so the best answer here is C. If you still have questions, post this one on Piazza and I'll talk about it further. All right, so for this question, which statement best describes a bonding molecular orbital? So now we're looking for something without a star, and it's going to be formed from the linear combination of two 2pz or two 2py atomic orbitals. This piece is important because it tells us it has to be this pi or side by side overlap. So we're looking for something that has a pi and no star. All right, so pi with a star has to go. Now we have to decide, is this bonding MO lower or higher in energy? Bonding molecular orbitals always offer some sort of a payoff in energy, so that tells us it has to be lower in energy. Otherwise, there's no reason for the molecule to do this. All right, this question asks you to scan the data table and find which second period homonuclear diatomic molecule had a bond order of 3. And that is going to be nitrogen, N2. So if we go along bond order, we see it's 3. And we could also calculate it because we see we have 1, 2, 3, 4, 5, 6 electrons in bonding MOs, and then we don't have anything in the anti-bonding MO, so we get a bond order of 1/2 times 6 equals 3. Which second period homonuclear diatomic molecule in the table has the shortest bond length? Well, this is going to be the one with the highest bond order. So because this was nitrogen in the last answer, I can skip to the chase and just say N2 is our answer. But if we take a second and actually track the bond length here, notice it decreases all the way to N2, and then it increases as we go to Ne2. All right, so following our theme here, which second period homonuclear diatomic molecule in the table has the largest bond enthalpy? Largest bond enthalpy means which one has the strongest bond. And if we look at bond energy enthalpy, all right, boom, we see nitrogen is going to be our winner once again. This question asks us to compare data for C2 and O2. All right, so here's C2, and here is O2. And this data set is interesting because both of these have a bond order of 2, but the bond energies and bond lengths are different. So notice that because oxygen has some electrons in this pi star orbital, it's going to destabilize it relative to C2, and we see this reflected in the fact that the bond energy is decreased. All right, so it doesn't take as much energy to break that bond. All right, so the best way to describe this one is that the double bond for C2 is harder to break because it has a larger bond energy value than O2. All right, really trying to drive this point home. A paramagnetic material is going to be attracted to a magnetic field, and it's attracted to a magnetic field because it has unpaired electrons. All right, in this question, this is really a review of some old material, but it's important to keep it fresh. If we're looking at an oxide ion, remember oxygen comes in with that helium noble gas core, 2s2, 2p4, okay? Oxide is going to have an extra electron, giving it a 2s2, 2p5, and we see that we've got 1, 2, 3, 4, 5, 6, 7 valence electrons. So you could have come right over here to the MO diagram and looked at the atomic orbital for oxide and counted those up. All right, this one has 3 questions in one. We're going to start with circling the bonding orbitals. Then we're going to go through and we're going to circle the anti-bonding orbitals. And then that will allow us to go through and calculate our bond order for peroxide. All right, so first, our bonding orbitals. Bonding orbitals are always lower in energy. So here we have a sigma 2s. If we go up to the 2p, we know that these are lower in energy. So we've got our sigma 2p from that head-to-head overlap, and then we've got the pi 2p. Now we have to count up the electrons, and we see that our sigma 2s has 2, our sigma 2p has 2, and our pi 2p has 1, 2, 3, 4. So 2 plus 2 plus 4 gives us 8 electrons in our bonding orbitals. If we go through and do the same thing for the anti-bonding orbitals, we see that we've got sigma star 2s, and we've got 2 electrons in there. And then we've got more up here, so our pi star 2p has 1, 2, 3, 4 electrons. So 2 plus 4 gives us a total of 6. This will allow us to calculate the bond order, which is 1/2. 8 minus 6 gives us a bond order of 1. So keep that in mind. O2 2- has a bond order of 1. All right, next question. Still picking on peroxide, O2 2-. Does it contain unpaired electrons? If we check paired, 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 and paired, so the answer to this first question is no. Because it does not have any unpaired electrons, it will not be attracted to a magnetic field. When it's not attracted to a magnetic field, this is diamagnetic. Okay, so this question asks us to compare a couple of different concepts we've reviewed in this lecture. And essentially we're looking for, is O2 2- with its bond order of 1, we calculated a couple slides back, is that going to be more stable than O2 with its bond order of 2? All right, so we can go through here and we can see that these two cancel each other out. This is the molecular orbital for O2. And we can see that we have our bond order is 1/2. We've got 6 electrons down here, minus 2 in the anti-bonding. So yes, our bond order is definitely 2. All right, so is peroxide more stable? I would have to say no, and the reason is that peroxide has a lower bond order, so this makes it less stable. So if we cross out everything that says yes, that leaves us with no, and then we got to pick the right reason. And it looks like B has the right reason. It's less stable than molecular oxygen because it has a lower bond order. All right, so this question's really bringing it home. What is the most accurate way to describe the OO bond lengths in the peroxide ion and molecular oxygen? All right, so again, this goes back to our bond order, which we determined from our molecular orbital diagram. We see that because peroxide has a lower bond order, it's going to have a longer bond. All right, so we're going to look for something that says longer bond. So this says shorter bond. This says longer. This says shorter. This one says longer. Okay, and then we've got to look for the correct reason. I'm going to look at D here. Because the peroxide ion has a lower bond order, that's going to be our correct answer. All right, so B is not correct because it says peroxide has a higher bond order. That's wrong. It's got a lower one.